Example 1 says, find the volume of the solid form by rotating the region bounded by y equals 2x minus x squared and the x-axis about the y-axis. Let's go ahead and graph this first. So here's my y-axis, here's my x-axis. I know that y equals negative x squared plus 2x is a parabola when I graph it, and it is a downward-facing parabola. And if I factor out an x, then that would leave me with negative x plus 2. And if I were to set that equal to 0, and I use the zero product principle, I would end up getting x equals 0 and x equals 2. So that helps me identify where my graph is crossing the x-axis. So here's 0, here's 2. And so my graph is going to look something like that. And we're bounded by the x-axis, and we're bounded by the x values, x equals 0 and x equals 2. So I'll just leave it at that. And then what I want to do is I want to rotate about the y-axis. So I'm just going to kind of do something like that to illustrate that we're mirroring around the y-axis. And so we get this three-dimensional shape when that revolution happens, and it kind of looks like maybe the upper half of a donut that doesn't quite have a hole in the center of it. I mean, it has a little hollowness, but not a complete hole. And so now what I want to do is I want to draw a rectangle that's going to kind of represent my shell. And what's happening is that that rectangle is being revolved around the y-axis. And I know that the thickness of this is delta x. And I need some other values for my shell. Now, if you imagine this shell being revolved around, it kind of creates this rectangle over on this side, and it is a cylindrical shell. So some values I'm going to need is I need the distance from the axis of rotation to my shell, which is actually our radius, right? And I'm going to call it r for radius. And then I also am going to need the height of my shell. I'll call it capital H for height. And that's going to help us in our formula, because essentially our volume is equal to the definite integral from a to b of 2 pi times the radius times the height. And then we're integrating with respect to x here. So let's figure out what these values are. Our volume is equal to, I can factor out 2 pi outside of my integral, and my limits of integration are from 0 to 2. And sometimes my students will get a little bit confused about what to make our limits of integration. And remember, it's kind of where our rectangles are starting and where our rectangles are ending. So my rectangles are going from here to here. And my students will ask, well, why are the limits of integration not negative 2 to 2? Well, the rectangles in quadrant 2 are already being accounted for because remember, these are cylindrical shells, and so they're already being accounted for when I'm counting or looking at the rectangles in quadrant 1. So my limits of integration should be from 0 to 2. And then my radius, I kind of blocked it with these pink rectangles, but our radius is the distance from my axis of rotation to an arbitrary shell, and that is just x, because here we're kind of thinking as this ordered pair as x comma y. So the distance from our axis of rotation to this ordered pair, that distance is x, and so that's my radius. And then my height is the y value, but we're integrating with respect to x, so instead of putting y here, I'm going to replace y with 2x minus x squared, and then we have dx. So this is the integral that would help us find the volume of this three-dimensional shape. So I've gone ahead and I've distributed in my x, and so my new integrand becomes 2x squared minus x cubed, and then once we take the antiderivative of that, we get 2 pi times the quantity 2/3 x cubed minus x to the 4th over 4, and we're evaluating this thing from x equals 2 to x equals 0, or the other way around. And so we get equals 2 pi times. The nice thing about this polynomial is if we evaluate it at 0, it'll just give us 0, so I really only care when we plug in 2. So I've gone ahead and I've done some simplification, and then finally if I multiply 2 pi times 4/3, I should get a final answer that the volume of this three-dimensional shape is 8 pi over 3. And that concludes this example. Example 2 says find the volume of the solid formed by rotating the area under y equals 1 over x squared, bounded by x equals 1 and x equals 2, about the line x equals 1. So here is a first look at an example where we're using shell method, and our axis of rotation is not the y-axis. So let's see how that's going to change things. We're only looking at the graph of y equals 1 over x squared in quadrant 1, so I'm going to just say it looks something like that. And I'm going to move it over a bit. So let's say this is 1, this is 2, so it's going to look something like that. And I'm only looking at it between 1 and 2, and then we're rotating about the line x equals 1. So that's this line here. That's going to be my axis of rotation. And so if I kind of reflect that, that's going to look something like that. And what I want to do now is I want to draw a rectangle. The thickness of that is delta x. And then the radius of this is the distance from my axis of rotation to my shell. So that represents my radius. And then the height is that dimension there. So let's call that h for height. So just as a reminder, I went ahead and I wrote my kind of setup integral. And so our limits of integration are going to be from 1 to 2. We have 2 pi. Now the radius in this case is not x because our axis of rotation is not the y-axis. So here's where folks often get tripped up. Let's call this point here x comma y, which tells us that the distance from the y-axis to that point is x. And I know that the distance from here to our axis of rotation, so the distance from my y-axis to x equals 1, that's constant, and that's just equal to 1. That's not changing. And so notice from this relationship that from here to here is 1, from here to here is r, and then the total distance is x. So if I'm trying to figure out what r is, I can tell from this image that 1 plus r is equal to x. So then if I solve that for r, I end up getting that the radius is equal to x minus 1. And we can kind of see that visually there. So my radius here is x minus 1. And then the height is just the y value. So because this point right here is x comma y, the height of my rectangular or my cylindrical shell is the y value, but we're integrating with respect to x, so I'm going to, instead of writing y, I'm going to write it as 1 over x squared, and then the thickness we can write as dx. So now what I'm going to do is I'm going to factor out 2 pi, and I'm also going to go ahead and distribute this 1 over x squared into both of those terms. So I've gone ahead here and taken the antiderivative, and we want to evaluate this. at x equals 2 and x equals 1. So I have the natural log of, now that I'm plugging in a positive number, I can just drop the absolute value signs. And we know that the natural log of 1 is 0. So then we get 2 pi times the natural log of 2. And then if I distribute this minus sign in here, I'd get 1/2 minus 1. So it looks like that's going to be minus 1/2. And here is our final answer for our volume.